All right. Well, welcome everyone to April's TEPS seminars. We have three TEPS trainees who will be telling us about their research. So I will let their advisors introduce them.
Hello, everybody. My name is Carissa. I'm a PhD student actually under John Moores here at York University, and I've had the great pleasure of working with Giang for many years, starting at our master's and now into our PhDs. He has a background in meteorology, studying the Martian polar caps before moving on to lava exoplanet atmospheres, which he will be talking about today. Don't want to give too much away, so Giang, feel free to take it away.
All right, cool. Just gonna share screen. All right, my name is Giang, and I'll be talking to you about the modeling and observing of lava planet atmospheres. So first I'll introduce lava planets. So lava planets are rocky planets that orbit very close to their star, and they orbit so close that the surface on these planets are hard enough to vaporize rocks. And so a thin atmosphere is created from the vaporization of the silicate dominant crust. And so being entirely locked, you have a permanent day side and a permanent night side, and there's a huge temperature contrast between the two sides. And so you would have essentially a lot of atmosphere on the day side and essentially no atmosphere on the night side. And this setup is actually very hard, if not impossible, for general circulation models to handle. And so much of the atmospheric modeling on these lava planets either focus on 1D radiative transfer or 1D horizontal hydrodynamics. And so let's talk about the radiative transfer work. So the evaporation of the magma ocean will likely generate a dominantly SiO atmosphere. And the thing with SiO, silicon monoxide, is that it absorbs ultraviolet light very well. And so it has a lot of heating in the upper level atmospheres. And so a lot of radiative transfer models show the temperature profiles of on these lava planets have a very strong temperature inversion. As for the hydrodynamics, a lot of the hydrodynamical models rely on surface turbulent boundary layer approximations. So you essentially have a flow driven by the pressure gradient of a lot of evaporation on the day side and deposition on the night side. And the thing is that since you essentially have such a large pressure gradient from having a lot of atmosphere to no atmosphere, this produces a very strong wind, and it produces supersonic winds. But these models assume an adiabatic temperature pressure profiles. And so we actually don't know how the strong winds will interact with the radiative transfer heating, especially from UV flux. And so, and then that's very important to understanding dynamics. So a lot of my work is to essentially take all these radiative transfer terms and jam them into this turbulent boundary layer models. And so this is the generalized form of it. You have the conservation of mass, momentum, and energy. And so we're gonna use this new model to explore the atmosphere on the lava planet K2141b, because that's one of the lava planet that James Webb will look at during its cycle 1. And we're also going to try and adopt different temperature profiles or parameterization that are consistent with the radiative transfer models. And so here are the results. So we did 3 main runs, one for an adiabatic temperature profile, one for an isothermal, vertically isothermal, and another one with a strong temperature inversion. And so you see that the pressure doesn't change. Oh, and this is with respect to the substellar point, the distance with respect to the substellar point. So 90 degrees is where you'd find the terminator. And so you find that the pressure for all 3 different profiles doesn't really change, but when you look at the wind speed, you see that there's more negative collapse rate. So that means temperature increasing with height, the winds get stronger, but the atmosphere actually gets cooler. So these wind speed, temperature, and pressure, they're measured or calculated at the boundary layer, layer's boundary. And you can think of that as near surface about half of the scale height. So why is it that the stronger the temperature inversion, the stronger the winds. And when you actually work out the math, a stronger temperature inversion will have a greater pressure gradient force, and that in turn pushes the wind further. And that actually also leads to cooling the atmosphere, because if we take a look at our energy conservation, so our total energy pretty much exclusively comes from the star, and that doesn't change what profile you use. And so when you have a lot more kinetic energy, a lot stronger winds, you have to decrease your thermal energy, or you have to cool down the atmosphere for the energy to be balanced. But you also notice a little neat thing, that after a certain while, the temperature for all three profiles will converge to be the same. And that has to do with the radial transfer. Here I'm showing the emissivity and the absorptivity of our atmosphere. And you can see that the absorptivity of ultraviolet light is pretty much 1 for most of the day side. So that means pretty much 100% of the star's UV flux is going to be absorbed by the atmosphere. However, in the IR, it drops considerably. And so when you near the substellar point, all the IR terms dominate, but the pressure will drop so much that after a while, ultraviolet radiation is the only thing that contributes to the energy balance. And so, so what ends up happening is that when the pressure drops really low, UV flux will start to heat up the atmosphere, but there's not enough infrared radiation to dissipate the heat. And so the only cooling term that will come into play is UV rated cooling, but that doesn't kick in until you get to really hot. And so what happens is that our atmosphere will just heat up by the UV flux until it hits a point where it can cool off in the UV as well. And so the temperature will sort of reach an equilibrium around 2600 Kelvin. So with all our results, we can actually simulate observables. And so here I'm showing you the transmission spectra, or the simulated transmission spectra. You see that the biggest feature lies in the UV, but it's actually still, the precision is still too great for any current instruments to measure. And so overall, the atmosphere of our modeled atmosphere is too thin, especially at the terminator, to produce a detectable signal. The emission spectra, however, is a lot more promising, and it shows strong SIO features within the range of James Webb and Spitzer. So here I also plotted how James Webb might observe this with NIRSPEC and MIRI. So NIRSPEC does pretty well, but not so much MIRI. But the important thing to note is that different temperature profiles produce discernible spectra. So a negative lapse rate or strong temperature inversions will produce a absorption feature, and the Keck, Spitzer observation seems to indicate so. While a positive lapse rate or an adiabatic profile produces an emission feature. And of course, there's actually a lot of caveats with this model. First is that they can't handle non-pure atmospheres, and therefore neglect complex chemistry, like especially around SiO and O, how they tend to split up and like stick together. Also, the thing is that a strong temperature inversion in the TP profile create a stable atmosphere and inhibits mixing. So our turbulent layer may not be as turbulent as we initially think. And also K214b actually has a very short period. And so you no longer have this axial symmetry from the substellar point to the antistellar point, because you have a lot of non-radial velocity component. And so Coriolis force is non-negligible at this point. But in conclusion, neat things to know about our new combined hydrodynamics and radiative transfer model is that near the terminator, so around 90 degrees, the atmosphere is horizontally isothermal, and that's due to the balance between UV heating and cooling. A strong thermal inversion leads to faster winds and an overall cooler atmosphere. And these actually translate to different emission spectra as well. And so for our future work, we hope to expand upon the model, add a more compositionally complex atmospheres. We can add sodium because it's very volatile, or oxygen because of just how quartz likes to split up into SiO and O. We also have assumed that the magma ocean is an endless source or sink of volatiles, and this isn't true. It also has its own saturations of things, and we actually don't know what the interactions between the atmosphere and the magma ocean is like. And finally, we would like to include cloud formation as well, because clouds actually will reflect a lot of visible light, and that's actually the most energy that gets pumped into the surface. Anyway, that concludes my talk. Thank you. I will take up any questions if there is any.
Thanks, Giang. Does anyone have any questions? One question I do have is, you mentioned with James Webb and how this planet is part of that first round. How are you expecting those results to really change what you are doing now?
Well, I mean, the biggest part is to see whether you do get, whether James Webb actually see an emission feature or an absorption feature, because it says a lot about whether or not the atmosphere is warmer or cooler than the surface. And I think that will probably be, well, it's very vital to understanding the dynamics of atmospheres in general. But yeah, so hope we get to see if James Webb can tell us that.
Great, well, good luck with that, and hopefully it does return some great science. Any other questions before we move on to the next speaker?
All right, I'm gonna stop share screen now and
hearing none. So yeah, let's move on. Bjorn, you're going to be introducing the next speaker.
Yes. Okay, so we basically have now two of my students speaking. That's Caroline Piaulet and then afterwards Stefan Pelletier. They're both PhD students with me. We're going to start with Caroline. Actually, both of these presentations will be presented also at Exoplanets 4 as plenary talks. So there will be 500 people or so listening to this. So if you have any, this is basically a dry run for this as well, good timing. So if you have any comments or any suggestions or anything, please write them down and send them to Caroline and Stefan. That would be highly appreciated. So Caroline is going to talk about her current paper, which is under review at Nature Astronomy. It's a paper on Kepler 138d, or the entire system. And yeah, I let her motivate everything and describe the results.
All right, thanks, Bjorn. Let me share my screen. Okay, so hi everyone, and thanks for the introduction. I'll just try to make my Zoom a little smaller. Okay. Yeah, so today I want to tell you the story of how the Kepler 138 system is opening for us a new window into what small exoplanets are made of. So as you all probably know, exoplanet science has demonstrated many times over that the diversity of planets we see in our solar system is nowhere near representative of how diverse we expect the outcomes of planet formation to be. And so understanding what types of planets can actually exist is one of the major goals of the exoplanetary science. And one of the most important results of surveys, especially the Kepler Transit Survey, is shown in this plot, which many of you probably have seen already. And it's focusing in on the small planet population. So the Earth would be around here and the size of Neptune would be around here. You're looking at the occurrence rate of planets as a function of their size. And so you have this very distinctive radius valley feature with the planets on the smaller size end, which we call super Earth, that have sizes that are broadly consistent with having a rocky composition. And the larger mini Neptunes have sizes that are large enough to suggest that they can't be only rocky, they're going to need to have some kind of gaseous envelope on top. But to really know what planets are made of, what we need is also mass measurements. So here we're looking at the same thing, but instead the planet radius is in the y-axis, and you see the radius value again. And what's interesting when you add this second dimension of mass is you can get first insights into the plausible compositions of a certain planet. And schematically speaking, in this parameter space, planets, so we have the super Earth and the mini Neptunes that we talked about before, and planets that are in this part of the parameter space would be considered consistent with having rocky compositions, while planets that for the same mass have larger radii than what you would expect for a rock would require to have some combination of hydrogen and or water or similarly dense volatiles. And so now in this framework of trying to understand what super Earth and mini Neptunes are made of, if we overplot on this diagram the measurements for the subset of the super Earth and mini Neptunes that I showed before that also have mass measurements, it roughly looks like this. So in accordance with what was expected, the wide majority of super Earth have measured masses that are consistent with being rocky, while mini Neptunes would need hydrogen or volatile-rich envelopes. So if we want to summarize what we know about small exoplanets, we have a good idea that super Earths seem to be rocky, at least those for which we have measured masses, while mini Neptunes would require some amounts of hydrogen and or water or volatiles to explain their sizes. But what we really only know is the compositions, or what we really only are starting to have constraints on are the compositions of small close-in exoplanets. And the reason for that is that to get the masses of small planets, usually we use the radial-velocity method, which becomes harder and harder to characterize planets as we get to longer orbits, so more warm-temperate orbits. And this is especially true for warm-temperate super Earth that are already small. And so we expect that the tug that they impart on their star is really small and very hard to measure. And so we don't really have radial velocity masses for these types of planets. And so this is a part of the parameter space that's very much to be explored. And this is why the Kepler-138 system was so interesting. So let me introduce the system. Kepler-138 is an M dwarf. You're looking here at the representation of the system. So like from the top down, the star would be at the center here. And there are 3 detected small transiting planets, Kepler-138b, C, and D, which are all very small, actually. They're all smaller than about 1.55 Earth radii. So they're all really in this Earth to super Earth regime. And what's really interesting about them is that they're also temperate in this kind of parameter space that we want to explore, with equilibrium temperatures ranging from 350 to 450 Kelvin for an Earth-like bond albedo. And what's also really cool about this system is that we can actually get the masses of these planets. Not necessarily via radial velocities, but because of the compact dynamical configuration that the planets have, where their orbits are in near resonant configurations that make it so that we can detect, or rather measure their masses using transit timing variations. The idea is that planets are going to perturb each other's orbit in a way that just using transits, we can see that transits don't occur for a single planet at a regular time intervals, but it's going to happen a little early or a little late. And how this varies over time is going to tell us basically what the mass of the perturbing planets are. And so for 3 temperate planets, for 3 transiting planets, we can get the masses of all 3 just from transits. To complement the data set of transits that had been observed with Kepler, we followed up the planets, so Kepler-138d, the ones that's closest to the habitable zone, using the Hubble Space Telescope with 3 transits, and the Spitzer Space Telescope with 10 transits. We also complemented our data set with 28 radial velocity measurements using Keck high-res, which enabled us to get upper limits on the masses and to double check that these were consistent with what we get from the analysis of the transit times. What you're looking at here is the transit time variations for Kepler-138d. So the way to read this plot is if you have a point over here, it means the transit was maybe 20 minutes late compared to a constant ephemeris. If it's around here, it means it was 20 minutes early. And this part is what we get from the Kepler coverage. And what's really interesting is that with our HST and Spitzer data, we get to see this third kind of passage from early to late transits, if we can call it this way, that really enables us to constrain very well the timescale over which these transit timing variations occur. And while the Kepler observations alone were actually consistent with there being only 3 planets in the system, as you can see with the dotted line that represents a model for that configuration, the 3 known transiting planets, we see that the timescale that we actually get from the new observations requires there to be a 4th planet, which actually has strong implications on the masses of the known planets in the system, and especially Kepler-138c and d, which are the super Earths that we're most interested in for now. So if we go back to this mass radius diagram and overplot all the known exoplanets, we can see that Kepler-138c and d are really interesting in that they are really one of the few temperate super Earth that actually have measured masses, but also the fact that they have 2 low densities, let's say they have higher radii for their masses than what would be expected for a rock. And what this means is that they need to have gaseous envelopes. It could be hydrogen, helium, it could be water or other similarly dense ices, or it can be a combination of the 2. That's something that we're going to explore. And the other thing that's also interesting is that both of them are in this configuration. So they're really twins. They have, within uncertainties, consistent masses and radii, and that can also tell us something about their composition. So first, if we explore the degeneracy of, well, is it hydrogen? Is it, let's say, hydrogen and water as a proxy for volatiles? Or is it a combination of the 2? What we did was using coupled detailed interior and atmosphere models to constrain the range of plausible composition. So that's what you're looking at in this plot. In this dimension, like in this y-axis, you see the amount of hydrogen, and in the x-axis is the amount of water, and the purple shaded area is what's consistent with the observations for Kepler-138d. Of course, as you expect, if you add more water, you're going to need less hydrogen, and conversely. But if you look at the edge cases, it means that the mass, radius, and temperature of Kepler-138d could be explained by it having 10 to 15% water in its interior plus atmosphere. But it could also equally well be explained by having just hydrogen, of course. But what's really interesting is the amount of hydrogen you'd need if no water is invoked. It's extremely small amounts. Actually, here we're looking at a hydrogen mass fraction of 0.01%, and we can place a 3 sigma upper limit on an amount of hydrogen of 0.1%. So now, just based on the mass and radius, we can tell these 2 scenarios apart. But because we have an idea of how much hydrogen or how much water there could be, now we can look at their viability of each scenario, because we can already imagine that having a 0.01% hydrogen atmosphere hold on to a 2 Earth mass planet might be problematic from an atmospheric escape standpoint. So if we start with this hydrogen-rich atmosphere scenario, what we did was use hydrodynamic models for the atmospheric escape of the upper atmosphere to estimate how long it would take for the planet to lose this amount of hydrogen. And what we find is that such small amounts of hydrogen and helium can be lost over timescales of the order of 10 million years. This is 2 orders of magnitude shorter than the age of the system. So we would need to be in a very fine-tuned state to be observing Kepler-138d as it's really shedding the very last amounts of its hydrogen envelope. And it's even more true that Kepler-138c, which is also at a different separation from its star, also has the same mass and radius. And so it would also have received different amounts of irradiation, but also have to be in the same kind of fine-tuned state. On the other hand, if we consider the second end case scenario where volatiles would be what make the planet have a low density, we could explain the planet with having about 11% water by mass, which is a significant amount of volatiles. We're talking about 50% water by volume. And now we could think that this is also potentially challenged by atmospheric loss, especially around an M dwarf star where we expect runaway greenhouse, especially during the pre-main sequence evolution where XUV irradiation is very strong. But what we found is that even in this scenario, because the reservoir of water is so important, this scenario would be stable against this early escape. So if we go back to our previous picture of what small exoplanets look like, Kepler-138 gives us a first hint that not all super-Earths are rocky. At least we know that Kepler-138c and D are most likely volatile-rich, although we don't know exactly which volatiles they're made of. But it's interesting in and of itself to know that planets below 1.7 Earth radii can just be assumed to be rocky. So as take-home messages, as I said, super-Earths that are not close in, but further out from their star could exhibit a wider diversity in their composition. For Kepler-138, both the transit timing variations, as well as the upper limits we get from the radial velocities, and the fact that the transmission spectrum from HST and Spitzer doesn't exhibit strong features that would rule out a high mobility atmosphere, this all points to the fact that Kepler-138c and D are volatile-rich super-Earth. And so finally, the idea is that some super-Earths could actually be warmer analogs of this volatile-rich icy moons in the solar system. If we're thinking, for instance, about Europa, Jupiter's moon that has about 8% volatiles by mass, if we put it closer to the sun, well, instead of having an icy crust, we would expect it to instead have a steam atmosphere the same way maybe Kepler-138c and D have. So that's it. And I'll take any question. Thank you.
Yeah, if I may. First of all, thank you, Caroline. My question would be, so if I understand correctly, you assume that the cores are Earth-like, so that the iron mass fraction is Earth-like. So my question is, how much confident that this is the case for this system or for super-Earth in general?
So what I showed in this plot is for an Earth-like rocky core, but we also have models that go up to iron-rich cores. It would mean that, for instance, we would need a bit more hydrogen and we would need a bit more water to explain it. But even in this case, you wouldn't have enough hydrogen. That's also something that we argue, but that I didn't go into detail in. So our models have iron, silicates, and then you can have water and or hydrogen.
Okay. Thank you.
I could give you the number of like how much hydrogen there could be, but I don't have it off the top of my head.
All right. If there are no more questions, then thank you, Caroline. And so we're going to continue with Stefan then. So Stefan Pelletier, he's also a PhD student in my group, and he will also give the talk at Exoplanets 4. So he will also appreciate any kind of comments that you have. We're changing gears a little bit. This is now high resolution spectroscopy with Maroon X. That's a new instrument on Gemini. And so he's going to show some nice results for hot Jupiter transmission spectrum.
Thank you. Yeah, you can see this well?
Yes.
All right, so as you can tell from my very long title, I have a lot of stuff to talk about. But yeah, I'm currently actually in Sweden at Lund Observatory as part of a TEPS internship. But I was feeling a bit homesick, so I had a quick Google search of what the weather was like back in Montreal. And surprise, surprise, it was raining probably as of yesterday, but just water rain. So that's probably not too bad. You can just have an umbrella. It could be worse. It could be on the exoplanet WASP-76b, where the forecast over there is iron rain, as you can tell from these headlines when this was discovered just about 2 years ago. Scientists discover planet where it literally rains metal. WASP-76, cloudy with a chance of iron rain. And so I hope you can already be intrigued by this planet, as certainly we were. So I'll start talking about this particular ultra-hot Jupiter. WASP-76b, so it's an ultra-hot Jupiter. It's like Jupiter, slightly less massive in mass, but like a lot puffier. So it has a radius of 1.8 times the radius of Jupiter. So it's around 6 times bigger by volume. And it only has a period of 1.8 days. So it's like if you take Jupiter and you bring it right next to the sun, it takes 1.8 days to fulfill a whole orbit, which means the planet will be tidally locked, kind of like the lava planet. And it has one side always facing towards its star and one face never seeing the light of day. And being so close, it's being blasted by radiation. And so it has a very high temperature. But the temperature is not uniform. Because it has a permanent day side, you actually get very high temperatures on the day side, and on the night side that actually never directly receives starlight, it can be quite cool. So like you can have over 1,000 Kelvin difference between the day and the night side. And so you have a big dichotomy of temperature regime between the permanent day and permanent night sides. And between the two, you have the terminator region, kind of the ring around the planet of atmosphere. It's kind of the transition between the day and the night side. And this is actually what we see when we probe planets via transmission spectroscopy. When a planet passes in front of its star and we look at it with a telescope, we probe this terminator region. So that's what we wanted to do with this planet. So we used the Maroon-X. It's a new spectrograph. You can see it down here. This is Andreas, one of our collaborators with the Maroon-X spectrograph. It's on the Gemini North Observatory. All you need to know is really it's a big mirror, so we get really good signals. It's a high resolution spectrograph covering 490 to 920 nanometers. So it's kind of most of the visible light and a bit of the near infrared at a high spectral resolution. So we're able to actually resolve spectral lines. And we used Maroon-X to observe 3 transits of the ultra-hot Jupiter WASP-76b. So what does the data look like? We get time series observations. So here I have a plot where on the x-axis is wavelength, and on the y-axis is exposure, or as a function of time. And there's a transit in there, but you have a time series of one spectrum after another while the planet is transiting the star. And this data includes the star that we're observing. Also, the telescope is on Earth, so you have to observe through the Earth's atmosphere. So there are some parts of that in the data. Obviously, we're observing a transit, so the planet signal will be in there. And of course, there's noise. So these are kind of the 4 main components that are contained in the data. And there are no stellar spectroscopists around. I'll tell you a secret. I don't actually care about stars. So the first thing I do with the data is I crunch the numbers to get rid of anything that has to do with the star and anything that has to do with the Earth's atmosphere. I don't really care about those. I want to look at the planet. And as you can see, the planet is over here. You don't see it? Well, actually, if you zoom in over here, let me help. If I zoom in over here, we can actually see this dark streak that's going diagonal. This is actually exactly the planet signal. As the planet transits, it's first coming towards you, then it's transiting, and then it's going away from you. So its signal is actually Doppler shifted. First blue shifted, so on the left, and then at the end of transit, red shifted. And this exact slopes corresponds to the speed, the orbital velocity acceleration of the planet. So let me zoom in again on on this line. This dark streak occurs exactly at 0.854 micrometers. That's a bit random, but if you look, this actually corresponds to a super strong line of calcium plus. So here you have the opacity as a function of wavelength for ionized calcium. And ionized calcium has a very strong line over here that matches exactly where this line is. So you can kind of already see by eye that we find ionized calcium in WAS76b. But this is not super scientific. We tend to normally do what we call a cross-correlation analysis. And the results of that is typically presented in what we call these KP-V-cis diagrams. So this is velocity on the X and on the Y axis. It gives you a 2D map. And how we fill this map, I'll try to explain over here. So we take our model spectrum at the bottom and cross-correlate it with the data at the top. And then we sum along the time dimension, assuming a planet orbit. And we pretend we don't know the planet orbit at the moment. So, and we try to fit this line over here. So I'll give one example. Let's say we try this line over here. It's not a very good fit. We're completely off. So that gives us a point over here on the data. And we can shift this line left or right and change the slope. Basically, we want to fit this line. So we can try something over here, move over there, try something over here. And eventually we get exactly the right slope. And now we fill this diagram, and this is what the results look like. So we can actually see there's this bright spot over here, and this corresponds to where we expect the planet to be. So if you have a strong signal, exactly where you expected it to be, then we claim there's a detection, in this case of ionized calcium on WAS76b. Now this is just for one element. We can actually repeat this process for all sorts of metals, ions, molecules, anything you think that will be on WAS76b, we can do a cross-correlation analysis and see if it's there. Now, here are the results of what we find. We find basically a lot of stuff. So from the top, we find very strong detections of iron, sodium, ionized calcium, as I showed, chromium, lithium, hydrogen, and the detections get a bit weaker, but still significant are vanadium, vanadium oxide, and so on. And at the bottom is what I would rate as more tentative detection: potassium, ionized barium, oxygen, and ionized iron. Now, all of this combined, this would probably make, as far as I know, the highest number of species that have been detected on an exoplanet so far, if all of these are true. But specifically of highest interest in here, I'll now focus on this VO, vanadium oxide. This is actually the first time that vanadium oxide has been discovered at high resolution on an exoplanet. And this species is actually of very high interest. Vanadium oxide is like the ozone on Earth. Ozone on Earth protects us from UV light from the sun. Well, vanadium oxide on ultra-hot Jupiters is like ozone on steroids. It really absorbs all of the UV invisible light. And so it's very good at heating up an atmosphere. And so if an ultra-hot Jupiter has vanadium oxide, it might have a very strong thermal inversion where the temperature will actually rise as you go higher up in the atmosphere. And we wanted to confirm this detection, and we're actually able to confirm it using a separate instrument, different transits, a different analysis method, completely independent. And we also see the signal right where we would expect it to be. So we're very excited about this. Another thing that we were quite surprised to see is this ionized barium. Obviously, this detection is a bit weaker, but if this is confirmed, this would actually be the heaviest element that has been detected on an exoplanet. If you look at our periodic table, it's way down over here with an atomic number of 56, where the previous heaviest element that I know would be of 38. So if this is confirmed, this would also be a very cool result. Now, let me come back and show iron. And those of you with the eagle eye may have spotted that I always put a little cross, and the detections that we have are always offset from the cross. And the cross is actually the literature value of what we would expect the planet to be. And you might be wondering, why is it a bit offset? And this might be puzzling, but remember the rain forecast? It's forecasting iron rain on WAS76b. If I come back to the original result that was published in Nature by Ehrenreich et al., this is a plot showing the Doppler shift as a function of time during transit of iron absorption on WAS76b. So the bright yellow streak over here denotes the signal of iron as a function of time in the rest frame of the planet. Basically, if you had a simple static planet with no winds, no rotation, you would expect the signal following this white line, and then the signal would be at the cross that I put. But instead, the signal was actually evolving in time and being more and more blue shifted, and you get kind of a kink. And this was interpreted as iron condensing out on one side of the planet. And this was the original result. Now, us with the Marunex data, we were actually able to confirm this result when I show also the Doppler shift as a function of the of phase or time. We can see the iron signal evolving into this kink-like thing. And this was originally interpreted as iron condensing out as the planet rotates. But if you also noticed, the other species seem to also be offset from the expected value. And when we did this plot using all of the other species, not including iron, we see that we also found a kink. So the original hypothesis that the kink-like behavior is due to iron condensing out of the atmosphere, well, it may not be so correct after all if we're seeing this for all of the other species. So it might be an independent process, such as clouds on one side of the atmosphere, that is causing this kink. But moving on, beyond just detections, we want to do more. We want to actually measure abundances. So I've been cross-correlating single templates, but if I put everything together, we get a very strong signal with all of the elements put together. And now I want to test how well my model matches this data. And I want to change my model parameters and do this like 1,000,000 times, testing every different parameter, changing the abundances, the clouds, the temperature, and see how things match. And then I want to measure the relative abundances and compare them to what we expect from chemistry. So here I'm showing at the top, we have the retrieved abundances. So we tested different models, tested different abundances. And so that's the posteriors we get at the top. We have magnesium over iron here and chromium over iron here. And at the bottom, we have our predictions from chemistry. So we just run a simple planet model at a temperature of 2000 Kelvin, and this is what we would expect. And we find that actually in these cases, what we recover is actually very much in line with what we would expect from our models. And then we can do this for other species, manganese and nickel. Nickel actually seems to be a bit super abundant. I'm not sure exactly why, but that could be interesting. Next, we have calcium and ionized calcium. Here we'd actually see that our models predicted a lot of calcium and just a little bit of calcium plus, but our data is showing the opposite. And so you might think, oh, like this is not really what we predicted. But actually, if you just tweak up the temperature, now I'll show a prediction for a 3000 Kelvin model. If we move up to 3000 Kelvin, then this actually matches very well what we would expect. All of the calcium is an ionized form, and you have very little calcium left in neutral form. Moving on, we have sodium, potassium, and lithium. All of these two seem to be a bit subsolar, meaning maybe some of it is ionized. And the lithium somehow seems to be a bit supersolar. I'm not sure how to interpret that yet. Here, if you have vanadium and vanadium oxide, these actually fall smack on to what we would expect, which, to be honest, was a bit surprising that they align so well with our models. But vanadium and vanadium oxide are actually very similar to titanium and titanium oxide. Now, titanium oxide is also something that acts as a UV absorber on ultra-hot Jupiters. But titanium and titanium oxide, we found that were very depleted. So this is what we would recover. We only recover upper limits. And our models predict that we should see a lot of it. We should see it all over the place. And our data is like, nope, no titanium over here. So just from this, we can tell that titanium seems to be severely depleted on WAS-76, begging the question, where is the titanium? As I said, titanium should be super abundant. It should be one of the easiest elements to detect, but we don't see even a peak of it. And if you go to hotter planets, we see it very easily. And so it seems like this planet is just quite not hot enough that perhaps the titanium is just condensed in the night side and it's trapped where we can't see it. And this is consistent with other planets where we see similar things, where the titanium just seems to be missing. So all in all, what have we learned? We learned that there are a lot of species on WAS-76b. We learned that VO, we've demonstrated that VO can actually be detected in exoplanet atmospheres at high resolution. We found that the kink-like behavior that was attributed to iron condensation may not be unique to iron, and it could be that something else is causing this kink. And we found that our retrieved abundances are almost always quite close to what we predict from our models, except titanium that is very severely depleted. So thank you, and I'll take any questions.
So I just have a very quick question regarding point 3 that you have here.
Yes.
So the kink-like absorption or the offset, you did mention that like this is not unique to iron. And because of that, you are making the logic that this probably not be purely from condensation, but like is the linking logic there that these other species cannot be condensing out because like at the altitudes where you expect this to be, the temperatures and pressures are not at the right level for those species?
Yeah, so basically this other species are like all of the other species combined. Yes, some of these could be condensing. In fact, they all have different condensation temperatures. And so it could be that all of these are somehow condensing, but the fact that the kink is very similar and all of these elements would have different condensation temperatures, it's certainly possible that it's partly the cause that some of these species are condensing, but other species are not expected to condense. And even in those species, we see this kink. So we suspect that it's something else. And there have been papers exploring this and having proposed other mechanisms.
Thanks.
Are there any other questions? Well, if not, thank you so much, Stefan. I think it really nicely shows now that with exoplanet atmospheres, we're not necessarily limited to one science case anymore when we take these observations, because there's so much different science in there. I hope that will also be like this with James Webb. So we're targeting one science case and at the same time resolving 3 other science or addressing 3 other science cases. I think this is quite nice to see here. All right.
Yeah, so I think I need to close this. Stefan, I also see some suggestions from Nick in the chat, so take a look.
Yep.
So I'm on the SOC of Exoplanets 4, so I probably read and reviewed your abstracts. Congratulations on making it. It was pretty tight. I unfortunately won't be there, but like I'm sure the conference will be great. And just to close this meeting, thank you to all 3 speakers for the really nice research overview. And the next TEPS seminar, Ahmad reminded me, will take place on May 11th. So watch out for emails from Ahmad. And that's it. So have a great day.